Deep within the constellation of Ursa Minor, a dead star is currently defying the fundamental laws of astrophysics by harboring a massive gas giant planet that absolutely should not exist. When I first looked at the latest spectral analysis released by the observing teams at the Keck Observatory, the numbers presented a startling paradox. We are looking at a planetary system located approximately 520 light-years away from Earth, featuring a star that has already lived through the most violent and expansive death throes of its life cycle. According to every established model of stellar evolution, the star has expanded far beyond the orbit of this newly confirmed planet. The planet should have been swallowed, incinerated, and completely obliterated millions of years ago. Yet the data confirms it is still there, orbiting peacefully, completely intact. This impossible survival creates a massive problem for our understanding of planetary dynamics and stellar life cycles. It forces us to ask whether our models of how solar systems die are fundamentally flawed, or if we are looking at the aftermath of a hidden cosmic event so rare and violent that it managed to save a doomed world. The exact mechanism behind this survival is hidden in the chemical signature of the star itself, a detail I will break down later in this analysis. But to understand why this discovery is sending shockwaves through the astrophysics community, we must first deeply examine the life, death, and internal physics of the star at the center of this mystery. The star in question is officially designated as 8 Ursae Minoris, though it is often referred to by the traditional name Baekdu, while its forbidden planet is known as Halla. I am analyzing a system where the primary star is currently in a phase of life known as the red clump. This is a highly specific evolutionary stage that tells us exactly what the star has been through. A red clump star is one that has entirely exhausted the primary fuel source of its youth. For billions of years, this star operated just like our own sun, fusing hydrogen atoms into helium deep within its core. This fusion process generates an immense amount of outward thermal pressure, which perfectly balances the inward pull of the star's own immense gravity. Astrophysicists refer to this delicate balance as hydrostatic equilibrium. As long as a star maintains this equilibrium, it remains stable, keeping its planet safe in predictable, quiet orbits. But the data from the recent spectroscopic surveys indicates that Baekdu exhausted its core hydrogen long ago. If you want to keep exploring these deep cosmic anomalies and track the ongoing unraveling of stellar mysteries with me as new data comes in, make sure to subscribe to the channel. When a star like this runs out of hydrogen in its core, the hydrostatic equilibrium is shattered. The outward pressure drops, and gravity immediately wins the battle. The core collapses inward, compressing the accumulated helium ash. As this core compresses, its temperature and density skyrocket to unimaginable extremes. This collapsing core releases so much energy that it ignites a shell of hydrogen just outside the core. This shell burning produces a massive surge of new outward thermal pressure, which pushes the outer layers of the star incredibly far outward. The star balloons into a red giant. The atmospheric layers expand dramatically, cooling down as they spread out, which shifts the star's emitted light toward the red end of the spectrum. I am directing your attention to the spatial dimensions of this expansion because it is the exact root of the current anomaly. When a star of this mass becomes a red giant, its radius swells to massive proportions, frequently reaching outward to a distance of 0.7 astronomical units. An astronomical unit is the average distance between the Earth and our Sun. The orbit of the forbidden planet Halla is currently locked at roughly 0.5 astronomical units from the star. This simple geometric contradiction is what challenges existing models. The radius of the star expanded to 0.7 astronomical units, but the planet is sitting at 0.5 astronomical units. The planet is located deep inside the maximum expansion radius of its host star, It should have been physically engulfed by the stellar plasma. The published research indicates that there is no margin of error in these orbital measurements large enough to explain away this overlap. The precise radial velocity measurements, which track the subtle gravitational wobble of the star caused by the orbiting planet, confirm the planet is exactly where the initial data suggested. I want to carefully explain the mechanics of this measurement so the severity of the problem is clear. When I review the high-resolution spectra from the observing teams, I am looking at how the absorption lines of the starlight shift back and forth over time. As the planet orbits the star, its gravity pulls the star slightly toward Earth, compressing the light waves and shifting them toward the blue end of the spectrum. As the planet continues its orbit and pulls the star away from Earth, the light waves are stretched, shifting toward the red end of the spectrum. By measuring the exact timing and amplitude of these Doppler shifts, astronomers can calculate both the mass of the planet and its exact orbital distance. The data shows a planet with roughly 1.5 times the mass of Jupiter, completing a perfectly circular orbit every 93 days. This rigid circular orbit, at half an astronomical unit, is undeniable proof of its location. So why does a red clump star present such a definitive death sentence for a planet at this distance? To grasp the severity of the situation, we have to look at the internal physics of the star during its red giant phase. As the star expands, the core continues to contract until the helium atoms are packed so tightly together that they reach a state governed by quantum mechanics. The electrons become degenerate, meaning they are squeezed into the lowest possible energy states. The laws of quantum physics dictate that no two electrons can occupy the exact same state, so this extreme crowding creates a new kind of outward force called electron degeneracy pressure. This quantum pressure is what temporarily halts the collapse of the core. However, the temperature inside this ultra-dense core continues to rise. When the temperature reaches approximately 100 million degrees Celsius, the helium suddenly ignites. Because the core is held up by quantum pressure rather than thermal pressure, it does not expand and cool when the fusion begins. Instead, a runaway thermonuclear reaction occurs. We call this violent event the helium flash. Within a matter of hours, an amount of energy equivalent to the entire energy output of our Milky Way galaxy is released deep inside the star. This violent flash finally breaks the quantum degeneracy, causing the core to expand, which ironically causes the outer layers of the star to shrink slightly. The star settles into the red clump phase, quietly burning helium in its core, which is exactly the state Baekdu is in right now. The fact that I am looking at a star currently burning helium proves beyond a shadow of a doubt that it already went through the massive red giant expansion and the subsequent helium flash. It already swelled past the half-astronomical unit mark. If the planet was there during that expansion, it would have entered the outer atmosphere of the star. Let us explore the exact physics of planetary engulfment, because understanding the destructive forces at play highlights why the planet's survival is so inexplicable. When a gas giant planet enters the outer envelope of a red giant star, it is subjected to an extreme form of aerodynamic drag known as dynamical friction. As the planet plows through the hot stellar plasma, its immense gravity pulls the stellar material toward it, creating a dense wake of plasma trailing behind the planet. The gravitational pull from this trailing wake acts as a massive brake, constantly bleeding away the planet's orbital kinetic energy. As the orbital energy is drained, the planet begins a deadly death spiral inward. It does not just orbit peacefully inside the star. The drag forces dictate that the orbit must shrink rapidly. As the planet spirals deeper into the denser layers of the stellar envelope, the friction increases exponentially. Simultaneously, the intense heat of the stellar interior begins to ablate the planet. The outer layers of the gas giant are boiled away, stripped off by the rushing stellar wind and extreme thermal radiation. For a planet with the mass of Jupiter, the entire process of inward migration and complete thermal destruction is incredibly fast on a cosmic timescale, often taking only a few thousand years. The planet is ultimately torn apart by tidal forces, and its chemical elements are completely absorbed into the stellar atmosphere. I often look for elevated levels of lithium in the spectra of old stars as a forensic fingerprint of recently devoured planets, because stars destroy their initial lithium very early in their lives. Any sudden spike in lithium usually means a fresh planetary body was just digested. But the detailed chemical abundance data for 8 Ursae Minoris shows absolutely no evidence of a recent planetary meal. The star's composition is relatively normal for its age and mass. The planet is intact. The star shows no chemical signs of engulfment. The orbital data is flawless. This profound contradiction forces us to discard the standard model for this specific solar system. The planet could not have survived inside the star. Therefore, the simple conclusion is that the planet was either never engulfed or it was not there when the star expanded. We must slowly peel back the layers of alternative hypotheses, each pointing to increasingly bizarre and fascinating orbital dynamics. The first theoretical escape route I want to examine is the possibility of extreme planetary migration. In the chaotic environment of a developing planetary system, planets rarely stay exactly where they formed. Through a process called planetary scattering, the gravitational interactions between multiple massive gas giants can become unstable. If 3 or 4 massive planets are orbiting relatively close to each other, their gravitational fields occasionally overlap in chaotic ways. This can result in one planet being violently ejected from the solar system entirely, becoming a rogue planet drifting through the dark void of interstellar space. Meanwhile, to conserve the total angular momentum of the system, the remaining planets are thrown into highly eccentric, highly elliptical orbits. Could Halla have originally orbited much further out, completely safe from the expanding red giant, only to be thrown inward after the star shrank back down? This idea presents a compelling narrative, but when I analyze the orbital mechanics required to make this work, severe flaws begin to emerge. If the planet was thrown inward from a safe distance, its new orbit would be highly elliptical. It would dive close to the star and then swing far out into the frozen outer reaches of the system. Over time, the tidal forces exerted by the star during those close approaches would slowly circularize the orbit, bleeding off the kinetic energy and shrinking the orbit until it became a perfect circle. However, tidal circularization takes an immense amount of time. It is a slow, grinding process. The data clearly shows that Halla is currently in a perfectly circular orbit. For the tidal forces of a single red clump star to completely circularize the orbit of a massive gas giant at half an astronomical unit, billions of years would be required. But the star has only been in its current helium-burning phase for roughly 100 million years. There simply has not been enough time for planetary migration and tidal circularization to produce the exact system I am observing today. The data stubbornly refuses to support the migration theory. Before we move to the next layer of understanding, we have to consider what remains uncertain about the nature of the star itself. What if our fundamental assumption about the star's solitary nature is incorrect? Throughout the galaxy, more than half of all sun-like stars are not solitary wanderers like our sun, but are instead bound in binary pairs, 2 stars orbiting a common center of mass. This brings us to the most radical, yet most scientifically elegant theory proposed by the research teams: the binary merger hypothesis. To understand how a second star could serve as a cosmic savior for a doomed planet, I need to walk you through a timeline of stellar violence that entirely rewrites the history of this system. Imagine this system roughly 1 billion years ago. Instead of a single star with a planet, we are looking at two stars. One star is slightly more massive than our Sun, and the second star is smaller, perhaps a red dwarf. They are orbiting very close to each other, locked in a tight gravitational embrace. Much further out, safely orbiting both stars, is the gas giant planet, Halla. Because it orbits the center of mass of the binary pair, it is completely stable, residing on the cold outer edges of the system. This type of configuration is called a circumbinary planet, famously resembling the fictional world of Tatooine with its twin suns. As millions of years pass, the larger star exhausts its core hydrogen first. This is a fundamental rule of astrophysics. The more massive a star is, the faster it burns through its fuel. The larger star begins its inevitable expansion into a red giant. As the primary star swells, its outer atmospheric layers reach outward. But before those layers can expand far enough to threaten the distant outer planet, they reach the smaller companion star. The gravitational domain of a star is defined by a boundary called the Roche lobe. Once the expanding outer layers of the larger star push beyond its own Roche lobe, the stellar material is pulled away by the gravity of the smaller companion star. This begins a dramatic phase of mass transfer. Plasma flows from the dying primary star onto the smaller secondary star. However, the expansion of the red giant is happening far too quickly for the smaller star to quietly absorb all the incoming material. Very rapidly, the outer atmospheric layers of the red giant completely envelop the smaller companion. This triggers one of the most complex and poorly understood phases in stellar astrophysics, the common envelope phase. I'm looking at a scenario where two stellar cores are orbiting each other inside a single, massive shared atmosphere of glowing plasma. And just like a planet moving through a stellar atmosphere, the smaller star experiences immense dynamical friction. The drag forces from moving through the dense shared envelope rob the smaller star of its orbital momentum. The two stellar cores begin to spiral inward toward each other. As they spiral inward, the orbital energy they lose is injected directly into the shared outer envelope in the form of kinetic and thermal energy. This injection of energy is the crucial turning point. The friction violently heats the outer layers of the shared envelope, causing the entire gas cloud to spin faster and faster. If the transfer of energy is violent enough, the outer layers of the stellar envelope are physically blasted away into deep space, exposing the tight binary core underneath. But in the case of 8 Ursae Minoris, the data suggests the two cores did not just survive as a tight binary. They collided. The orbital decay continued until the smaller star physically merged with the helium core of the larger star. This stellar collision was catastrophic, creating a single, completely new stellar core with a suddenly increased mass. This massive influx of fresh hydrogen from the smaller star disrupted the standard evolutionary track of the dying red giant. The merger event abruptly halted the expansion of the star. It never reached its maximum predicted radius. It never grew large enough to engulf the distant planet. The violent fusion of the two stars created a single, rejuvenated star that immediately settled into the red clump phase, quietly burning helium, mimicking the appearance of an older, solitary star. The planet Halla merely watched this chaotic merger from a safe distance. It was never engulfed because the primary star was stopped before it could finish its lethal expansion. The binary merger effectively short-circuited the red giant phase. This elegant solution perfectly matches the observational data I am analyzing. It explains why a seemingly older, post-expansion star hosts a planet at a desperately close orbit. The orbit of the planet never changed. The planet has always been sitting at half an astronomical unit. It was the star that failed to expand past that point. The true mechanism behind its survival was the sacrifice of an unseen companion star. But this binary merger hypothesis, while brilliant, opens up an entirely new set of questions about planetary formation that pushes the boundaries of current astrophysical theory even further. If we assume the binary merger took place, we are forced to look at the debris left behind. When two stars merge inside a common envelope, an enormous amount of stellar material is violently ejected outward into the equatorial plane of the system. This massive cloud of cooling plasma, rich in heavy elements, dust, and gas, forms a dense, swirling disk around the newly merged central star. This structure is called a circumbinary disk. When I look at the physical properties of this disk, it bears a striking resemblance to a protoplanetary disk, the exact same kind of structure that surrounds newborn stars and gives birth to fresh planets. This introduces the most shocking hypothesis of all. What if the planet I am observing is not an ancient survivor, but an incredibly young second-generation planet? Let us explore the mechanics of second-generation planetary formation. We know that planets form through the slow accretion of dust and gas within a disk. Microscopic dust grains collide and stick together, eventually forming pebbles, then boulders, then planetesimals. If the core of a newly forming planet reaches a critical mass, roughly 10 times the mass of the Earth, its gravity becomes strong enough to rapidly pull in the surrounding hydrogen and helium gas, eventually swelling into a massive gas giant. This process typically takes millions of years and occurs when a star is newly born. But the debris disk generated by a stellar merger provides exactly the same raw materials and the exact same physical conditions. The data allows for the possibility that Halla did not exist when the two stars were orbiting each other. It was only after the stars collided and ejected their outer envelopes that the planet began to form. Within the dense, chaotic, swirling debris field of the dead stars, a new core accreted. It swept up the heavy elements forged in the hearts of the dying stars. It vacuumed up the ejected gas, slowly growing into a massive gas giant right there at half an astronomical unit, perfectly circular, formed from the ashes of a stellar collision. This second-generation hypothesis explains every anomaly in the data perfectly. It explains the perfect circular orbit, because a planet born within a disk naturally forms with a circular orbit. It explains the proximity to the star, because it formed after the star had already finished its chaotic merger and settled into its current size. When I evaluate these two dominant theories, the ancient survivor saved by a stellar merger versus the newly born second-generation planet forged in stellar debris, I am looking at a profound shift in how we understand planetary resilience. For decades, the astrophysical community assumed that the death of a star was the absolute end of its planetary system. The engulfment physics were considered an undeniable death sentence for any world unfortunate enough to be orbiting too close. But the data beaming down from telescopes observing 8 Ursae Minoris proves that the universe is far more creative and far more chaotic than our basic models suggest. The implications of this discovery stretch far beyond a single distant star system. This data forces us to reconsider the ultimate fate of our own solar system. In roughly 5 billion years, our sun will exhaust its core hydrogen. It will lose its hydrostatic equilibrium. The core will collapse, and the outer layers will balloon outward into a massive red giant. The expanding solar plasma will easily engulf Mercury and Venus, vaporizing them completely. The fate of Earth has always rested on a razor's edge in these calculations. Some models suggest the sun will expand just enough to swallow the Earth, while others suggest the sun will lose enough mass through solar winds that its gravitational grip will weaken, allowing the Earth to slowly migrate outward to a safe distance. But our sun is a solitary star. It has no binary companion to plunge into its outer envelope and halt its expansion. Our sun will experience the full, devastating red giant phase without interruption. Therefore, the survival mechanisms I am analyzing for the Forbidden Planet will not apply to Earth. However, the existence of second-generation planets forming from the debris of dying stars presents a fascinating vision for the distant future of the galaxy. Even as older stars die out, their death throes create the exact conditions necessary to birth entirely new worlds. Planetary formation is not restricted to the dawn of a star's life. It is an ongoing cyclical process that can happen even in the shadows of stellar corpses. The ongoing analysis of this highly unusual system will rely heavily on next-generation observatories. Instruments like the James Webb Space Telescope and the upcoming extremely large ground-based telescopes will be uniquely positioned to analyze the infrared signatures of systems like this. I will be looking specifically for residual dust rings or faint thermal glows that might indicate an ongoing second-generation accretion process. By carefully studying the chemical composition of the planet's atmosphere, if we can isolate its spectrum from the blinding glare of the host star, we might find exotic chemical ratios that prove it was formed from the heavily processed metal-rich debris of a stellar merger rather than the pristine hydrogen clouds of the early universe. Every new data point we collect from this forbidden planet forces us to refine our mathematical models of dynamical friction, common envelope evolution, and orbital mechanics. The survival of Halla is a massive puzzle piece in the broader map of exoplanetary demographics. It shows us that dead stars are not just static monuments in the night sky, but dynamic, evolving environments capable of hosting complex planetary systems. We are moving from a simplified view of solar system evolution into an era where we must account for stellar collisions, atmospheric drag, and debris disk planetary formation, all interacting simultaneously. If you found this deep dive into stellar dynamics and orbital physics valuable, leaving a like helps push this highly detailed scientific analysis to a wider audience of curious minds. As I continue to monitor the incoming data streams from astronomical surveys around the world, I expect to find more of these impossible planets. The universe rarely produces only one anomaly. Where there is one forbidden planet, there is likely an entire hidden population of strange surviving worlds orbiting dead and dying stars, waiting to be discovered by the next sweep of our instruments. The boundaries of what is physically possible in astrophysics are constantly being tested by the silent, steady data coming from the dark corners of the cosmos. The survival of this gas giant orbiting a dead star is not just an error in the data. It is a loud, undeniable signal that our understanding of stellar evolution is incomplete, and the true chaotic nature of the universe is far more magnificent than we ever predicted.